other session. I'm going to make our first speaker a co-host so that they can share their screen. Benji. So if you want to try that, thanks.
Sure. Can you hear me okay?
Okay, so we're ready to get started with our parallel session 1. Our first team is Team SANCHO, and they'll be giving a talk entitled Modeling Structured Heterogeneity in Small Populations, a COVID-19 Hospital Case Study. So Team SANCHO, you can take it away.
Thank you, Juniper. She basically did most of the work for my first slide for me. So as touched on last week, and basically like Juniper said, we're trying to model the heterogeneity in a smaller group, specifically a hospital in Northern Florida. And to that end, we are modifying the traditional SEI compartment model by adding an infectious compartment as well as a quarantine compartment to account for the healthcare workers that are removed soon after becoming symptomatic. And then we're also creating a rewiring rate, omega, which is going to be proportional to the fraction of infected people in the population, reflecting behavior change in the hospital, the way that healthcare workers respond to other healthcare workers when they suspect that they're getting symptomatic, which is a very real thing, particularly right now with COVID. We'll go over our analytical results, and then we'll show you an agent-based model in Python that we coded up, very early stages. And we're also going to be using an ergom approach with actual surveys administered to the healthcare workers. Jumping into the traditional SEIR compartment model, we have tweaked it quite a bit. This is the ideal version of what we're doing. I'm not going to go over all the details because that would be the whole 7 minutes. But the short version here is basically in the hospital. This is really the pathway, given the probabilities for each one of these transitions that most healthcare workers are going to be going through. Namely, the majority will be infectious asymptomatic, and then the infectious symptomatic component, when they transition there, typically will not remain in the hospital the entire time and go through the recovered stage because of the high surveillance in hospital. Most of them are going to end up going into the quarantine class. And then over the period of 14-day quarantine, they will eventually come back in either as susceptible, exposed, recovered if they were actually quarantined, and we're pulling in people from replacement workers. I'm sorry, I misspoke. The replacement workers will be replacing those who go to the quarantine class. So we have those arrows at the top coming down into each compartment to represent that. As far as the adaptive rewiring, we're making that component omega a function of infecteds. So this middle susceptible person right there links up to two others, becomes infectious asymptomatic, and then makes them exposed. What basically happens when that infectious asymptomatic red dot right there becomes symptomatic, even though he might be connected to two people he infected who don't know it yet, he's now symptomatic. The hospital workers see that. The two red dots basically disconnect, assuming we set omega to 1, which would mean maximum disconnection. We can tune that. And then that hospital worker that was symptomatic is quarantined with a 1-day delay, and the previously asymptomatic people rewire, which is a bit of a problem. They rewire and they infect more people. And then this process basically goes on and on and on, affecting both the network structure and the spread of infection through different healthcare workers. This is the hospital, just to give you a big view of it. Bird's eye, 1,100 bed hospital separated by 3 buildings, total N of 4,700. We've split up the 3 buildings into grids, and then those grids we have separated in the ABM into 3 separate towers. This is the again, kind of a bird's eye view of them. This is specifically a sped up representation of the actual ABM that we have. This is about 10 times speed. You can see these black dots here represent each a unit on the hospital. So this could be ICU, this could be the ED, and we have the SEIR with both infectious and asymptomatic components running down here. This is just to give you kind of an overview of what we have, and you'll see as time goes on down here, this green line, which is susceptible, starts to come back up as people are being replaced in the population. I have the SEIR graph statically in the next slide, so you guys don't have to catch all of this second by second. This is just to give you an idea of the interface that we have for the ABM. So like I promised, this is the SEIR graph with a half-day delay right now built in for replacement of symptomatic infected healthcare workers with non-infected symptomatic healthcare workers from outside population. You can see here, mimicking what was in the dynamic version, that susceptible population rebounds. We are still working with the parameters on this to get it really tuned in. But these are hot off the press results this morning. One thing that we have found analytically is that our R0, even with this adaptive omega rewiring rate, our R0 is not changed by that, but it is dependent on the ratio of SI edges to I edges. So basically the number of susceptibles that are connected to infecteds over the total number of infecteds. And these two vine lines here, this top one is the R0 graph with some oscillations near the end that we have to sort of deal with. But these two vine lines show how down here, this is the SI to I ratio, correspond with where the R0 stabilizes. Right now, the R0, the actual absolute value, is not representative of the system because we have some basic assumptions built in about healthcare workers being totally connected at the level of units, which will be changed moving forward. We also have an ergom approach that we're doing in parallel with a little bit more of a top-down view on behavior of the healthcare workers, and we have a survey which we designed here. These are some of the questions you'll see about personal protective equipment use, number of contacts in a day, how long those contacts last, how often people travel to different areas in the hospital, like cafeterias. The ergom conception of the hospital, we split it into 3 buildings, pretty similar to the ABM. Then those 3 buildings have movement between them. Each building has floors within it, and then each floor, for the ergom, we are kind of conceptually splitting it up broadly into patient care, non-patient care, and mixed. And then from there, we are going to let those broad functional categorizations do their adaptive magic. We are still working on the parameterization for that ergom model. That data was more schematic. We are tweaking the epi model R package to be able to accommodate adaptive rewiring. Moving forward, these are the things we're going to do next. We need to finish the moment closures to really capture the full SEIR with quarantine and omega system. We need to build in true adaptive rewiring to our ABM and remove some of the assumptions we have that make our R0 incorrect. And then we need to actually administer the survey and get data from the hospital, for which we have an IRB submitted. And that's it, guys. Thank you. Any questions?
Great, thank you. If you have any questions, you can please write them into the chat, or you can unmute yourself. All right. All right, thank you, Benji.
Okay. Thank you.
And Team Sancho. Okay. Next up, we have Team Infodemic Dynamics. So I think Jihi is going to be sharing their screen if you want to. Oh, or Amy. Okay, make you a co-host.
Okay, and I'm going to unmute our other presenters.
Okay.
Okay, I think we have everybody.
Okay. And if you want to just try to share your screen before I introduce you.
Sure thing.
All right. Okay, great. Now we can get started. So next up, we have Team Infodemic Dynamics, and they'll be presenting a talk entitled 5G Kills, a case study of COVID-19 misinformation on Twitter. So take it away.
Hi, so this is Infodemic Dynamics, and we're conducting a case study of COVID-19 misinformation on Twitter. Anti-5G conspiracy theories have existed since as early as 2016, but you may have only recently heard of them since they've seen a spike in popularity during the pandemic. Specifically, conspiracy theories linking 5G and COVID-19 have spread across social media, with celebrities and public figures amplifying these messages. So these are no longer obscure fringe theories, they're becoming increasingly mainstream. And they've had real-world impacts such as the destruction of cell towers. And this also has significant implications for public health, as we've seen in recent and ongoing protests against lockdowns and physical distancing measures. So we're taking two complementary approaches to identify and characterize narratives, and these are word embeddings and topic modeling, as well as word co-occurrence and community detection. And next we'll go into our data collection and analyses.
Our sample included tweets that were made between January 1st and April 15th, which contained the string 5G surrounded by a word boundary. Originally, we planned to do a multilingual analysis, but we found that the majority of tweets containing the term 5G were in English, so we decided to focus on English language tweets. And as you might expect, we do see a heavy tail on the distribution of user activity, with some users being very active during this time. The most active users include a range of brands, news outlets, and also accounts which are spreading anti-5G misinformation. We do see a notable spike in the mention of 5G, particularly following COVID-19 officially being declared a pandemic. And we see a further spike in April following reports of cell tower arson and harassment of telecom workers. In addition to changes in the volume of tweets, the topics being discussed are changing over time as well. So in the next section, we'll take a closer look at how discussions about 5G have changed during the COVID-19 pandemic.
So first, we used a word embeddings-based approach. Word embeddings are basically vector representations of words. And it makes it easier to cluster the words together or see the similarity. So these are two graphs that show the results from February 2020 and April 2020. We showed this before as well last week. So as you can see, in February, the narrative was around clusters of innovation, services, data, encryption, just one turn deceiving, but then that was also not related to the COVID conspiracy. But as soon as we enter April 2020, the clusters are around corona, conspiracy, risk, psychopaths, attack. You can see all these terms in the TSNE graphs. TSNE graphs are basically visualization techniques to show something of a high dimension to a lower dimension. We use 300 dimensional word embeddings here, and we show them to 2D. Next is heat maps. These heat maps are also showing something interesting. These are showing the similarity between the different words. We chose tech, phone, innovation, 5G, and startup. In January 2020, between all these, 5G is the odd one out. In March 2020, innovation is the odd one out, which is surprising because COVID hasn't apparently not much to do with all these terms, but it did show some similarity according to the vector representation, and this shows that then how the narrative evolved from January to March. That's it.
Besides the vector embeddings, we also use network embeddings of the words in the tweets, connecting words that appear in the same tweets. We can use these word co-occurrence networks to examine how the usage of words is changing and how words are being grouped together into topics. We can use node measures like PageRank to examine if a word is in the core or periphery of the conversation. And we can also use the inverse of clustering coefficient, specifically 1 minus the clustering coefficient, to see whether that word is being used consistently in a single type of narrative or in multiple different types of narratives. And separately, using community detection methods on these networks, we can identify the topics of conversation. First, we see here in these figures that we have different measures of nodes changing over time, and that can help us track the narrative around those words. So we can see here that coronavirus and hashtag coronavirus follow similar trends, but have differences near the end. So that might tell us something about how people are centralizing around a certain way of talking about a thing in a narrative. Then we also can see things like security and future, which were related to previous concerns before the coronavirus about the security of the 5G system under the Huawei company. And those are taking a downturn. We'd like to see if the networks can tell us more about how to predict stuff like that and how to analyze it. And also we noticed that things like the advantages of 5G have also taken a downturn, such as the advantages that would come with an Internet of Things that would be made more accessible with the 5G technologies. Next, we'll look at how we can use word co-occurrence networks to do black box topic modeling. So what we can see here is we created a network from these word co-occurrence occurrences in the tweets, and then we can apply different community detection methods after we pruned the network by removing words that occur less than, or connections that occur less than once a day on average. And it's really early in the results now, but we're getting some interesting and promising qualitatively groups that are being made, such as the topics being able to break up different branches of the conspiracy, because there are branches that are concerned with the 5G as like a direct safety issue with radiation. And then we also have things that relate it to COVID-19. And it'd be interesting if we can reliably tell those different types of conversations apart. And it seems like we might be able to, but we have more work to do on that. As we see the infodemic changing, we can say that it's destructive and dangerous behavior in the news, but because the disease is spreading at the same time and can be aided by less drastic behavior in the population, we'd like to examine those effects.
So now we'll turn to the implications of this work for pandemic mitigation. Recent studies from the UK examine the relationship between conspiracy theory beliefs and compliance with recommended prevention strategies, including social distancing and hand washing. Both of the most recent studies from the UK find a strong association between the endorsement of conspiracy beliefs and low compliance with public health guidance. The endorsement of a 5G conspiracy belief was the most strongly associated with non-compliance with public health guidance for COVID-19 prevention. And next, I'll discuss the relationship between conspiracy theory endorsement and public health behaviors, including infection risk. Given that we know these variables are linked, Swamy and Barron suggest taking action to support active rejection of conspiracy beliefs. Prior agent-based models explore the concept of inoculation against misinformation and disinformation campaigns, and that inoculating even a small percentage of the population by prohibiting them and spreading misinformation may be sufficient to mitigate pandemics. Future work should explore what inoculation actually looks like in real-world settings and what the ethical implications of a strategy such as inoculation might be. In conclusion, it's important to understand the spread of misinformation during pandemics in order to control disease spread. Thank you, and we'll take questions.
Great, thank you guys so much. We have a couple of questions inside the chat. The first question asks what community detection methods you used.
So I checked, I did actually like a ton of them, and they mostly gave consistent results. I'll tell you which ones I looked at. I did like the fast greedy modularity optimization, and let me tell you. Fast greedy modularity optimization, infomap, leading eigenvalue, label propagation, multi-level, edge betweenness, walk trap. But the one that I used for the slides was using the spin glass method. But they all gave mostly consistent results, but I just picked one.
Great. And we have one more question in the chat that's asking why 10 is one of the highest degree words on April 15th, but not earlier. Is this some sort of important number to 5G conspiracy groups?
No idea.
Okay. Good. All right. Thank you all so much. If there's any other questions, you can type them into the chat. If not, we'll move on to our next presentation.
Gia might know that though.
I'm not so sure. Maybe it's I've seen some conspiracy theories have these code words or code hashtags that are pretty obscure, but they're kind of like secret indicators like Agenda 21. So it could be, but we don't know.
Great. All right, so we're gonna move on to our next team, Asym and Dyst. I believe Blake is sharing their screen. Okay. And I'm gonna redeem myself with this word. Okay. All right, let's get started. So our next team is Asym and Dyst, and they'll be giving a talk entitled Interactions Between Asymptomaticity and Social Distancing.
Hello, I'm Upasna, and we are Team Asym and Dyst with Blake Williams, myself, Ulrike Hahn, and Nicholas Roberts, and we are exploring the interrelations between asymptomaticity and social distancing. So now that we are into this crisis for about 5 months, there's a lot of information we have about COVID-19, but one of the central features that is still surrounded with a lot of uncertainty is the proportion of asymptomatic individuals. Estimates are going, studies are going around to have an estimate of this proportion of asymptomatic individuals, but it is seen to vary a lot. There is a wide range. So one study claims that the proportion of asymptomatic individual is around 5.8%, whereas another study claims that 4 out of every 5 cases is asymptomatic. So given that the majority of the transmissions remain undocumented, it is important that the proportion of asymptomatic individuals is taken into account in the studies because they do shape the spread of the disease during an epidemic. Hence, our research question is to explore how the unknown proportion of asymptomatic individuals influence the reduction of transmission of the disease via social distancing. The framework that we use is Percolation framework. So what are percolation networks? So basically, given a network, we go through every edge of that network and we keep that edge with a probability equal to the transmission rate of the disease, and we delete it otherwise. The resultant network is called the percolation network, and it basically consists of all the edges that for sure will spread the disease from one end of the edge to the other if either of the nodes get infected. Now, for an epidemic to occur, it is important that the percolation network has a giant connected component, because the number of nodes present in that giant connected component of the percolated network basically gives us the number of individuals who ultimately get infected by the disease. Here is a figure you can see on the left that shows the infected red nodes who belong to the giant connected component. On the right, you have 2 plots. The plot above has average degree in the x-axis, and the plot below has the percolation probability, which is basically the transmission rate of the disease. And on the y-axis, we have the number of nodes that belong to the giant connected component of the percolated network. We see a very interesting phase transition happening right after average degree goes above 1 and right after transmission rate goes above 0.2, when the number of edges in the percolated network is just enough to have majority of the nodes belong to the giant connected component. So the takeaways from these simulations is that both the degrees of the individuals of the network and the transmission rate of the disease play a very important role in deciding the occurrence of the giant connected component, which in turn gives us the number of individuals who ultimately get infected during an outbreak.
Now that we understand a percolation framework is useful, how do we model asymptomatic infections? We can do this by simply assigning each new infection to be symptomatic or not, according to some probability. We chose to model a difference in behaviors through a modified transmission rate, which we assume will be higher in asymptomatic cases, since by our assumption, symptomatic persons will be more likely to isolate if they know they are sick, reducing transmission relative to asymptomatic cases. We're able to determine analytic results for epidemic thresholds under the following set of assumptions. First, we assume the contact network has Poisson degree distribution, as is true for Heterogeneity networks of large size. We specify the proportion of asymptomatic infections new, as well as the transmission rate for symptomatic and asymptomatic cases. We define the symptomatic transmission rate to be some fraction gamma of the asymptomatic cases. Although transmission may actually be more likely for symptomatic persons, we use the parameter as a proxy for a reduced number of contacts as they isolate. From these transmission rates, we can derive R0 and C critical, the average degree of contacts above which we expect an outbreak, a threshold which we are trying to dip below through social distancing. Here we see the mean degree required for an outbreak according to this analytic model. The y-axis is the asymptomatic infection proportion, the x-axis is the asymptomatic transmission rate, and the contours show the degree required for an outbreak as a function of these. The figure on the right shows us what happens when the difference between symptomatic and asymptomatic transmission rates are much greater than that of the figure on the left. In brief, what these figures are showing us is that the transmission rates become more dissimilar. The proportion of asymptomatic cases ends up mattering a lot more. With this analytic model, we are also able to decompose the infections into those resulting from asymptomatic and symptomatic transmission. This allows us to determine how important asymptomatic spread is during an outbreak as a function of the asymptomatic infection rate and the differences in transmission probabilities. Here we're looking at the contribution of asymptomatic cases. Again, the asymptomatic proportion is on the y-axis with the ratio of symptomatic to asymptomatic transmission rates on the x-axis. The best way to look at this plot is to start on the right-hand side where transmission rates are equal. As you move left, you increase asymptomatic transmission rates relative to the symptomatic transmission, and you see more and more cases are caused by these asymptomatic infections. Now, this is a fairly intuitive relationship, but we demonstrate the rate at which that change occurs here. Now, the other thing this framework allows us to do is to look at the probability of an outbreak instead of the outbreak threshold, demonstrating the probabilistic nature of this model. As before, more dissimilar transmission rates implies that asymptomatic cases matter more. We can also view the probability of an outbreak as a function of the average degree in the contact network. This is a useful analysis given that we're able to control the mean degree through interventions like social distancing. Now for future work, we will be conducting analyses based on networks of finite size as compared to the infinite case here. We will vary contact networks with symptomaticity, whereas thus far we have accounted for that by different transmission rates. And we want to inform our model with data. This includes the distribution of degree for the contact networks, the transmission rates, as well as the asymptomatic proportion of the population. Thank you for your time, and we'll take any questions.
Great, thank you, Team Asym and Dyst. If there are any questions, you can either type them into the chat box or unmute yourself. Okay. Thank you all. We have our last presentation coming up, and this is from team All You Need Is PageRank. I believe, who is sharing their screen for that one?
I am going to share my screen. Can I?
Yes, you can go ahead and share your screen, and then I'll introduce your team.
Okay, can you see the slide?
I can. Okay, great. So our next team who will be presenting is All You Need Is PageRank, and they'll be presenting a talk entitled Topology of Commuter Flows Between Geographies, a wrap-up and follow-up. So take it away.
Hi, all you need is PageRank. The only purpose of this project is better decision making. As we are done with meta-population model, we dive into topology of commuter flows between geographies. And here is a brief overview of problems addressed in this journey. We have an aggregated month of intercity commutes between Russian cities, flights, trains, buses. It makes a graph of nearly 1,000 nodes connected by 20,000 weighted edges. First thing to do was an implementation of that meta-population model. So we treated each city separately, plus we considered traffic flows. Next question is funnier. Which city has the biggest impact on dynamics? And here you can see a map of Russian railroad networks. In case it is the only city, PageRank is all you need. As we want to find several cities that maximize spread, the question is trickier. This problem is NP-complete, and good news is there are good approximations. So we use this recent stop and stare algorithm to find suboptimal places to control or block. Next, we look at higher order structures, motifs. We know that in nature, there are recurring patterns of interaction. We also know those patterns are not random. For example, there are 13 possible directed structures of 3 nodes. And the test for this non-random nature is simple. We count motifs, rewire original networks so that nodes preserve their degrees, and count motifs, randomize many times, and get expected frequencies of structures to appear at random. An important property of networks is structural roles. Nodes are embedded differently. So we take counts of motifs around every node, which stands for a city, and use them as feature vectors to mingle later on. For every node, we look at its neighbors. That is how we combine a neighborhood for a few hops. As we define neighborhood, we start collecting information about those nodes, and those are motif count vectors. We make aggregation for first variant linearly, and it is an implementation of Rolex algorithm. And then we do a non-linear aggregation, which is basically a graph convolution network. So next thing to do is to test whether or not it works. And first test we run is TSNE projection to make sure whether or not those embeddings are positioned in some structure. Next, we clusterize those embeddings in order to find out similar structural roles for nodes. And we find somewhat 7 alike roles for cities. Does it make sense? It seems so. We can see that Moscow gets into a cluster of 1, and St. Petersburg and Ekaterinburg, those are major Russian cities, they fall together. Next thing we do, we plot those structures on the map, and we can see that it seems to be reasonable. At least we can see that this line of violet colored nodes, it corresponds to Trans-Siberian Railway. As we see that linear projection works, we move on to non-linear projection, and we know that graph neural networks, they produce embeddings of smaller size and better resolution. And a reminder that inside is a linear combination of neighbor feature vectors, some extra parameters, and non-linear activation of the result. And next thing we do, we split layers of this network by transport type, and we make linear projection, those are top 3 pictures, and non-linear projection. We can see that non-linear projections make better resolution, so nodes are separated wider, so that later on when we do a downstream task like clusterization, when we collect together like roles or defining communities, would produce better results because nonlinear models make better discretion of embeddings. Next thing is motif structure of each network alone, and it gives us a hint for future improvement, just as we did first iteration and used motif count vectors as blind features. We can do a smarter move and use only those significant motifs. And here we can see that for every substructure defined as a adjacency matrix 3 by 3, we have organic frequency count and as z-score, and z-score is how many times this motif is more often than at random. So here we arrive to first point of our journey. We want to improve decision making, and in order to do so, we have to combine embeddings for cities and not only find structural roles, but we want to compare structures of regions so that authorities of alike communities could exchange relevant knowledge because tactics vary. And a thing that helps is an old algorithm of Weisfeiler-Lehmann test for isomorphism, which is an old coloring algorithm that produces an embedding for entire graph. And so far we tested it and we got quite good results on the downstream task, which is our second objective. We want not only to define some alike regions and cities, but also we want to improve downstream regression task. At the moment, major Russian bank runs a machine learning contest where participants have to predict how many infections and casualties are going to happen next week. And as context is about to finish, participants are sharing their models, and we have started embedding those topological features into winning models. And I think the 10% improvement of loss function is something great, and it gives us a reason to do a follow-up. So that first thing to do would be benchmark against existing baseline like Node2Vec and VERSE, which are good unsupervised embedding producing algorithms. And second thing to do is to do something smarter other than just taking bag of motifs. And next thing is basically primary purpose for me to be interested in structural embeddings and unsupervised learning, because I work as a consultant on business transformation, and I use a tool for assessment of structural changes for myself. Now I'm trying to put this pet project to serve the society as medics are facing major change of structures and processes around them. And as people face disruption, as organizations restructure, they find themselves in unusual position, they get stressed. So those structural embeddings are a good way to reason not only which structures are very much alike, but also we can apply dialectic thinking and say that if we have a valid measure for structural similarity, it is going to be as good for dissimilarity between structures. So that once a node had changed environment, we can predict stress by this distance it has to travel. And I think it's a reasonable measure. So there is a lot of things to do. So that's it. Let's move on to questions.
Great, thank you so much. If you have any other questions, you can type them into the chat, or you can unmute yourself and ask them now.
Moment. Let me check the chat.
I don't think there are any questions in the chat.
I'm doing unpopular things. What can I do? Representation learning on graphs is very unpopular thing nowadays.
Well, thank you so much for your presentation. That was the last talk of our session. So thank you all so much for being here. And it's just been an honor to watch all of these projects as they grow and develop. And I can't wait to see your abstracts in the next few weeks. So thank you all so much. And I'll see you in the Slack. All right. Bye, everybody.